Welcome to today's lesson. We're going to continue talking about area, but we're going to move from polygons talking about circles. We're going to focus today on arcs and circles and finding arc measures and arc lengths. And in the next lesson, we'll get into more of the area of circles. Now, before we get into this, though, I do want to take a moment to review the formulas that we've learned so far. At this point, I'd like for you to pause the video, review these, and hopefully get them, write down as many as you can, and then restart the video and review the formulas that you have with the ones that I put up. If there are any that are incorrect, you can then correct those. Hopefully you got most of these correct. If not, please correct the ones that you didn't have, fill in the ones that you didn't have, and continue to practice and learn these so that we have them ready to go as we go through these problems. Now, as we move into today's discussion, we do have to cover some vocabulary. Some of these will be familiar, some of them will not. Please take this time to pause the video, and if you haven't already done your vocabulary cards for this section, you can do those at this point. Okay, as we move into talking about arcs, we're going to first learn how to name arcs. We're going to start with semicircles because they tend to be the easiest to identify. Then we're going to talk about minor arcs, and then we're going to talk about the major arcs. Now, semicircles, remember, they come from our diameter. So in this figure, we have a diameter of AE. There are two semicircles associated with it, the one above the diameter, the one below the diameter. If we look at the one above the diameter, we can use either letter that comes between A and E, so either B or C. So we have semicircle ABE. I could also call that semicircle ACE. It's the same thing. If we look below the diameter, we have ADE. Now, if we go to semicircle or to the diameter CD, two semicircles associated with that. Above the diameter, we have DAC, or we could alternatively call that DBC. We have also below that diameter, semicircle DEC. For every diameter, there's always two semicircles because the semicircle is half of the circle. When it comes to the minor arcs, remember, these are the arcs that are smaller than a semicircle. So we want to go just kind of around the circle methodically. If I start at A, I have AB, that's definitely less than a semicircle. I also have BC, which is less than a semicircle. I also have AC. Even though it goes past B, that's still less than a semicircle. Now, if I go to AE, then that gets into a semicircle. I don't want that. I do have CE, and I also have BE, both of which are less than a semicircle. I can then continue on around my circle. If I go to CD, that's a whole semicircle, so I don't want that. But I can do ED, or I'm going to put them in alphabetical order, DE. I also have AD as I continue around my circle, and BD or DB, depending on how you look at it as you continue to go around the circle. All of these are minor arcs. And we typically list the minor arcs first because they're very helpful in identifying the major arcs. Major arcs are going to go the other way. So if we look at AB as the minor arc, the major arc is going to be the other part. And you can pick any other letter to name it. So we still have the endpoints of A and B, but we're going the other way around the circle. So we're going to identify that by putting a point in the middle. So I'm going to call it ADB. Now next we have BC, so I'm still going to have the endpoints of B and C, but we're going to go the other way around the circle. So I'm going to use, again, D because it's a good letter. It's right there in the middle. Next we have AC. We're still going to have endpoints of A and C, but we're going the other way around. I can't use B because that's the minor arc, but I can go the other way. So I'm going to use E this time. So we have AEC. Then we have CE. Going the other way around the circle, we have CAE. BE, going the other way around the circle, we could have BAE. DE, going the other way around the circle, DAE. You can use one of the other points if you'd like. That's okay. AD, if we go the other way around the circle, we have ACD. And finally, BD, if we go the other way around the circle, BCD. All of these are now major arcs, and they're easy to find once you identify the minor arcs first. So naming arcs is pretty easy. We're going to move into how to find arc measures and arc lengths. The arc measure comes from the measure of the central angle. It has the same measure as whatever that central angle is. If it's the minor arc, we can look at that. If it's the associated major arc, we can simply take the whole circle, which is 360, subtract from it the part that we already have to find the major arc. A semicircle, because it's half a circle, is always going to be 180 degrees. And just like in Chapter 1 when we talked about segment addition and angle addition, we also have arc addition. So if we have two adjacent arcs, meaning they don't share any common points, so we have AB and BC, they don't share any common parts of the circle, we can add them together to find the measure of arc ABC. So let's look at an example of how to do this. If we find the measure of each of these marks, if we start with arc BC, we're told that this central angle is 32, so that arc's going to have the same measure, so it's also 32. For BD, that's BC plus CD. BC we know is 32. CD we're told is 58. So we do 32 plus 58, and we get a measure of 90. Now ABC, when we look at that, that's a semicircle because we have diameter AC. All semicircles have a measure of 180. And if we look at arc AB, that's this part right here. Well, I know that the measure of arc AB plus the measure of arc, BC is going to be the same as the measure of arc ABC, which is good because I know BC and I know ABC. So the measure of arc AB plus, if I substitute in 32 for the measure of arc BC, equals 180 because that's the measure of our semicircle ABC. Subtract 32 from both sides. The measure of arc AB is 148. Works the same as the segment addition. We just did it a little backwards. Now this also comes in with circumference. If we're looking basically at arc length, the circumference is the entire circle. It's the entire arc. You guys have seen this formula before, depending on whether you have the diameter or the radius, and that's different only because we know the diameter is 2 times the radius. So it's really the same thing, just kind of depends on which information you're given. You can use either formula. Some of the problems that we do are going to ask us to round. Some of the problems are going to ask us to leave the answer in terms of pi. If we leave the answer in terms of pi, then you're going to have an answer like 8 pi, where we don't multiply 8 times 3.14. In addition, you're going to see some problems that talk about concentric circles. These are coplanar circles, meaning they're in the same plane, that have the same center. So they're different sizes, but they share the center. This next problem that we're going to look at talks about coplanar circles because we're looking at the tracks that a camera dolly runs around as it's going around a movie scene. In this example, the radius of the inner circle is 8 feet, the track is 2 feet wide, and we want to know how much farther does a wheel on the outer circle travel than a wheel on the inner circle in one turn. Now we're talking about going around the circle, so we're going to use circumference. In this case, I'm given a radius length, so we're going to use 2 pi r. We're going to start by finding the circumference of the inner circle. Then we're going to find the circumference of the outer circle, and then we're going to compare the two. Now again, we've got 2 times pi times the radius. Now my radius in this example for my inner circle is 8. So 2 times pi times 8, I get 16 pi. For the outer circle, we're still going to use 2 times pi times the radius. My radius for my outer circle is going to be the inner circle plus the distance between the two. So I have a radius of 10, which means the whole circumference is 20 pi. Now we want to know how much farther the outer wheel travels compared to the inner wheel, so we're going to do the difference. So we're going to take 20 pi minus 16 pi. We get a difference of 4 pi. Now that doesn't mean a whole lot to us in terms of feet, so we then put that in our calculator to estimate. If I round to the nearest hundredth, I get 12.56 feet. So it's traveling approximately 12.5 feet more than the wheels on the inner circle. Now if we look at arc length, we're going to use circumference to help us basically find a percentage of the actual circumference that's being traveled. So if we look at this first example, we're going to use a formula here where the length of the arc is the measure of the arc over 360, which gives us the percentage of the circle, and we're going to multiply that times the circumference. And it doesn't matter which part of the circumference we use. That's going to depend on what we're given. So in this first example, we're going to have the measure of the arc, which is xy, divided by 360, and we're going to multiply that times pi times the diameter because we're given the diameter. Now the measure of the arc we're given is 90 degrees because it's a right angle. So 90 over 360 times pi times 16. 90 over 360 reduces to 1/4 times pi times 16. We're going to leave the answer in terms of pi. So all I'm going to do is multiply 1/4 times 16. That gives me 4. I still keep the pi because I'm leaving my answer in terms of pi, and my unit is inches. So I have 4 pi inches as my final answer. Let's do a couple more examples just like that. For number 5, we're given a larger arc. This time it's a major arc that we're given. So same idea, we're going to find the measure of the arc XPY, divide that by 360 to get the percentage of the circle, and then we're going to multiply that times the circumference. For this one, we're given the radius, so we're going to use 2 pi r. Now the measure of the arc is 240. Divide that by 360. Multiply that times 2 times pi times 15 for our radius. Now if I do that multiplication, I'm going to get 240 divided by 360 times 2 times 15. I can do all of that on the calculator. I get 20. Leaving the answer in terms of pi, so I'm going to leave pi. My unit is centimeters, so my unit is centimeters. So we have 20 pi centimeters as the length of that arc. For number 6, same idea. Now we have a semicircle with a radius of 1.3 meters. Again, we're going to leave our answer in terms of pi. So we're going to go with the measure of our arc. I'm going to call it AB because we're not specifically told, times our circumference. Now it's a semicircle, so the measure of that is always 180 divided by 360 times 2 times pi times the radius of 1.3. Now 180 over 360 reduces to 1/2, so I have 1/2 times 2, which cancels itself out because 1/2 times 2 is 1. So we're left with 1.3 pi. My unit is meters, so my answer is going to be in meters. It's that simple. I hope you've enjoyed this, and I'll see you in class.